start putting some values to these forces. So we start with the hydrostatic pressure. And to keep things simple, I'm going to keep referring to this as the push force. Now, the hydrostatic pressure in the capillary is kind of the unique variable here because it's going to decrease as we go from the arterial end to the venule end of the capillary. So this one value, this capillary hydrostatic pressure, there are actually two values as we look at the movement from the arterial end to the venule end. So at the arterial end, the capillary hydrostatic pressure is usually about 38 millimeters of mercury. And by the time we get to the venous end, we've lost that pressure. And we already talked about why we lose that pressure, right? From arteries to veins, we have a pressure gradient. So by the time we get to the venous end of this capillary bed, the hydrostatic capillary pressure has dropped to about 60 millimeters of mercury, okay? But we know that the movement here favors filtration, okay? And that's the movement from the capillary out into the interstitial space. The other force that we have to take into account in regards to hydrostatic pressure is the interstitial fluid hydrostatic pressure. And that is usually very negligible. That's the force that the interstitial fluid is exerting on the capillary. So pushing fluid from the IS into the capillary. And that's usually 0 to 1. So this favors absorption, okay? Now, let's talk about netting out these forces. So on the arterial end, we're going to subtract the higher force, the higher hydrostatic force, and then we subtract the lower hydrostatic force. And this gives us a net of about 37 millimeters of mercury. So that is our net hydrostatic pressure at the arterial end. Okay, very clear. The net hydrostatic pressure at the arterial end. And if we do the same thing at the venous end, we take 16, subtract out our smaller pressure, which is the IS pressure. Our net pressure at the venous end is 15 millimeters of mercury, okay? But this is only half of the picture, right? This is only the hydrostatic pressure. So let's look at the osmotic pressure. Any questions so far? Just flag me down if I've lost you, if anything here sounds confusing. Okay, so we talked about the hydrostatic pressure, we net those two values out. The osmotic pressure or the oncotic pressure or the colloid pressure, basically in the capillary it's going to be quite high because we have proteins that are in the capillary that cannot cross the capillary wall. And so that's about 25 millimeters of mercury, and that favors reabsorption, right? Remember, that's a pull. So we're pulling fluid from the IS into the capillary. In the interstitial fluid, the IS oncotic pressure is very negligible, and we talked about why. There aren't that many proteins or non-permeating solutes out in the interstitial space. So that's about 0 to 1, and this favors filtration because, again, we're pulling fluid from the capillary into the interstitial space. And so if we look at the gradient here and we subtract 25 and we take away 0, which is our negligible IS oncotic pressure, we get about 25 millimeters of mercury as our net osmotic pressure, and this favors absorption, right? This is movement from the interstitial fluid into the capillary. So that movement favors absorption. So what we can see here is that our four opposing forces, we have a larger capillary hydrostatic pressure and a larger capillary oncotic pressure, okay? And what that tells us is that the movement on the arterial end is usually going to be in favor of absorption, and the movement on the venous end is usually going to be in favor of, the other way around. The movement here is going to be in favor of filtration, and the movement here is going to be in favor of absorption, okay? So basically that makes sense. If we are diffusing materials, oxygen, nutrients across the capillary bed, we need a filtration force more dominant on the arterial end. And as we get closer to the venous end, we want to reabsorb carbon dioxide and other metabolites. And so we have a stronger force for absorption over towards the venous end. Okay, yep. The movement on the arterial end is more in favor of filtration. Filtration, okay, I apologize. Okay, so everyone got that right. So on the left end or the arterial end, we're filtering substances i.e. pushing substances out of the capillary. And on the venous end, we are absorbing substances, materials back into the capillary, so absorption. Okay? But in order to sort of prove this for ourselves, we can look at each of the values and actually calculate to make sure that this is true, because we just threw this slide up here, but we didn't actually calculate it out, net out those pressures to see that this is true. So let's look at netting that out. Before we do that, any questions? Any other questions? Okay. This may be a little bit confusing as we look at it for the first time, but hopefully as we go on, you can clarify any questions. Okay, so we're gonna put all four of our forces together and we're gonna calculate the net filtration pressure, sometimes called the NFP. Okay, this is the net filtration pressure. And this is going to actually prove to us that what we said was correct, that filtration does indeed take place at the arterial end and absorption does indeed take place on the venous end. So I'll draw a similar diagram. We have our tissue on this side. And an arterial here. Okay, this is the arterial end. I'm sorry, our capillary here. This is the arterial end, this is the capillary. And this is the venous end. Okay. Let's remind ourselves of these forces once again. So we have the oncotic pressure, which is a pull. And the hydrostatic pressure is a push. Okay. All right, so let's start to fill in our relevant forces. Now we know that the capillary, let's draw this in red. The capillary hydrostatic pressure, which is a large P, changes as we go from the arterial end to the venous end. That's sort of the first thing. Okay. It's about 38 millimeters of mercury here, and by the time we get down here, it is 16 millimeters of mercury. We also know that there's a second hydrostatic force. That's the interstitial fluid hydrostatic force. So the interstitial fluid hydrostatic force is usually about 1 millimeter of mercury. Okay. And let's just remind ourselves of the direction here. So this is a push force going that way. This is also a push force going that way. And this is a push force going this way. Okay, so these are our hydrostatic pressures. Now, capillary hydrostatic pressure is the only one that has a gradient from arterial end to venule end. So let's just make that clear. This is the only one that really changes. Let's look at our osmotic pressures. So the first one we have is the interstitial fluid osmotic pressure. And that we said is negligible. It's going to be 0 millimeters of mercury. And that is a pull force pulling fluid towards the IS. And then we also have a capillary oncotic pressure. And that is also a pull force pulling fluid into the capillary. And that is usually higher at about 25 millimeters of mercury. Okay. All right. Any questions so far? Any questions so far? All right. So let's do the math down here. So let's calculate these pressures out and actually see what the net pressure is and what the net direction of fluid movement is. So let's start by looking at the arterial end. And then we'll look at the venule end. And so the formula for net filtration pressure is filtration minus absorption. So we can basically plug in the forces that favor filtration. So what forces favor filtration? To get you guys to help me out. What forces favor movement of fluid from the capillary out into the interstitial space? Yep, so the capillary hydrostatic pressure. What else favors filtration? The interstitial fluid osmotic pressure, perfect. Okay, and then that gives us our other two forces that we know favor absorption, which are our interstitial fluid hydrostatic pressure and our capillary oncotic pressure, okay? So all we do is plug in the variables here. So we know this is 38 plus 0, and we subtract out 1 plus 25, right? So we're just plugging in our variables. Capillary hydrostatic pressure, interstitial fluid osmotic pressure, interstitial fluid hydrostatic pressure, and then our capillary oncotic pressure, okay? And that gives us 38 minus 26, which is about 12 millimeters of mercury. Now, we can either look at the actual numbers to determine the net movement of fluid, or we can just look at whether the value is positive or negative. So either of those methods would tell us what direction the force favors. So because this is a positive number, but also because filtration is a bigger value, we know that this favors filtration. Okay. And we can do the very same thing over on the venule side, on the venule end. So once again, NFP is filtration minus absorption, which is the same. I'll plug it in here. So capillary hydrostatic plus interstitial fluid oncotic, interstitial fluid hydrostatic plus capillary oncotic, okay? And that gives us 16, right? Remember, our capillary hydrostatic pressure is now less on this side. So this is the only value that really changes as we get to the venule end. So we've got 16 on this side plus 0, which is our same interstitial fluid osmotic pressure, and we subtract out our other two variables, which is 1 for interstitial fluid hydrostatic pressure and 25 for capillary oncotic pressure. And that gives us 16 minus 26. So right away here, we can see two things. One, the bigger value is absorption, but also when we do this math, this is going to wind up being a negative number, okay? So that will also tell us that on this side, we favor absorption. Okay? So basically, when we look at each of the pressures and we net them out on the arterial end and on the venous end, we can prove here that at the arterial end, the general net direction of fluid movement is filtration. And to remind ourselves, filtration is fluid moving from the capillary out into the interstitial space. And then on the venule end, we're going to be absorbing fluid from the interstitial space back into the capillary.